Now, here is something that trips people up almost every single time. You hear the word light year, and your brain immediately files it under time. Years, that is a unit of time. You think someone is talking about how long ago something happened, how far back in history we are reaching, how many years something took, and I understand why the brain does that. The word year is sitting right there in the middle of the phrase, bold as anything, practically demanding you interpret it as a duration. But here's the thing, a light year is not a measure of time at all. Not even a little bit. It is a measure of distance, pure geometric spatial distance. The confusion comes from the fact that the universe is so staggeringly large that the only sensible unit for measuring its distances involves borrowing the concept of time to express how far light travels. And light, as we will get into, moves faster than anything we have ever built. Faster than anything physics even permits us to build with conventional methods. So when we say a light year, we mean the distance that light covers in 1 year of constant travel. That is the definition, distance, not time. Now let us put some numbers on that, because this is where things start to get uncomfortable in a very satisfying way. Light moves at roughly 186,000 miles per second, not per hour, per second. In one single tick of the clock, light has already traveled a distance greater than 7 times around the entire circumference of the Earth. Now hold that image for a moment. In the time it takes you to blink, light has lapped our planet multiple times over. It is almost offensive how fast that is. So if you let light run free for 1 full year, 365 days, all day and all night without stopping, the distance it covers comes out to roughly 5.9 trillion miles. Some people round it to 6 trillion miles, and that is close enough for our purposes today. 6 trillion miles, 6 followed by 12 zeros. That is what a single light year represents in physical space. Now, I want you to really sit with that number, 6 trillion miles. Your brain will not do it naturally. Human brains did not evolve to process numbers at this scale. We evolved to count berries and track prey across the savannah. The cognitive machinery we are working with was not designed for cosmological arithmetic. So, let me help you feel the weight of this through an analogy that is a little closer to human experience. Imagine you are standing on a beach in California, and someone tells you to swim to Japan. The Pacific Ocean is roughly 7,000 miles wide at that point. Now, you are a strong swimmer. Let us say you can move through the water at about 2 miles per hour if you are really pushing yourself. You start swimming, you kick your legs, you pull through the water with your arms. You are working hard. You feel like you are moving. And relative to your body, you are moving. But relative to the size of that ocean, you are practically a motionless speck sitting on the surface of an enormous spinning ball of water. Your progress is so tiny compared to the total distance that the whole exercise starts to feel less like travel and more like a cruel joke played on you by geometry. That is the feeling I want you to carry as we talk about interstellar distances, because the situation we face with space travel is not just similar to that ocean swim. It is incomprehensibly worse. So let us talk about the fastest thing we have ever launched from this planet. Voyager 1 is a spacecraft that left Earth back in 1977. It has been traveling continuously ever since. It has left our solar system, which is already an astonishing achievement, and it is currently the most distant human-made object in the history of our civilization. Right now, Voyager 1 is moving at approximately 38,000 miles per hour. 38,000. That sounds like a lot. When you hear that number, you might imagine something impossibly fast, something streaking across the sky faster than you can follow with your eyes. And compared to a car on a highway, yes, that is blinding speed. A commercial airplane cruises at around 550 miles per hour. Voyager 1 is moving roughly 70 times faster than that airplane. By human standards, we built something extraordinary. But now let us do the mathematics that matters. We have a distance of 6 trillion miles. We have a speed of 38,000 miles per hour. How long does the trip take? You divide the distance by the speed. 6 trillion divided by 38,000 gives you approximately 155 million hours of travel time. Now, that is a big number in hours, but it still does not feel visceral enough. So let us convert it. There are 24 hours in a day, so divide by 24. You get roughly 6.4 million days. Divide that by 365 days in a year, and you land at approximately 17,500 years. 17,500 years. Let that settle. At the speed of our fastest spacecraft, traveling nonstop, never slowing down, never needing fuel, just coasting through empty space, it would take over 17,000 years to cover a single light year. On a single light year. And our nearest stellar neighbor, Proxima Centauri, the closest star to our sun, sits about 4.2 light years away. That means even getting to the nearest star in the entire galaxy would take our fastest spacecraft somewhere in the range of 73,000 years. Not 73 years, not 700 years, 73,000 years? Modern human civilization is only about 10,000 years old. We would need to leave Earth, maintain continuous spacecraft function, and travel for a duration that is 7 times longer than the entire recorded history of human society just to reach the closest single point of light in the night sky. Now let us talk about why we cannot simply go faster. This is where the physics of propulsion becomes the real villain of the story. Every rocket we have ever built, from the earliest fireworks to the Saturn V that carried astronauts to the moon, to Voyager itself, runs on chemical propulsion. You take a fuel, typically a combination of a propellant and an oxidizer, you combust them together, and the exhaust gases shoot out of the nozzle at high velocity, pushing the spacecraft forward. This is Newton. Action and reaction, forces in opposite directions. It works. It is elegant in its own way, but chemical propulsion has a fundamental problem that is baked into the physics, and there is no engineering trick that removes it. The problem is this. To accelerate a spacecraft, you need fuel. But fuel has mass, and mass requires more fuel to accelerate it. So, the more fuel you add to go faster, the heavier your spacecraft becomes, and the more fuel you need to accelerate all that extra fuel. This is called the Tsiolkovsky rocket equation, and it is one of the most sobering pieces of mathematics in all of aerospace engineering. The relationship between fuel mass and achievable velocity is not linear. It is exponential. To double your final speed, you do not simply double your fuel. You need to multiply your fuel load by a staggering factor. The math turns against you in a way that makes chemical rockets deeply inadequate for interstellar travel. To reach even a small fraction of the speed of light, say 1% of the speed of light, which would be about 670 miles per hour, a chemically propelled spacecraft would need to carry an almost absurd ratio of fuel mass to payload mass. We are talking about a spacecraft that is almost entirely fuel with a tiny sliver of actual spacecraft attached to the front, and even then, you are only at 1% of the speed of light. At 1% of light speed, that 4.2 light-year journey to Proxima Centauri still takes 420 years. Better than 73,000, but still well beyond any single human lifetime or even many generations. And this is the part that I find most revealing about our actual position in the universe. It is not just that space is big. Lots of things are big. What matters is the relationship between the scale of space and the maximum speed that matter can travel. Einstein showed us that as an object with mass accelerates, it gets harder and harder to push faster. Not just harder in a practical sense, but harder in a fundamental, deep physical sense. The closer you get to the speed of light, the more energy you need to add to keep accelerating, and the gains in speed get smaller and smaller. At light speed itself, a massive object would require infinite energy. This is not a technology limitation. This is not an engineering problem waiting to be solved. It is a fundamental geometric property of space-time. The speed of light is the absolute ceiling for anything with mass, and reaching even a meaningful fraction of it demands energy budgets that are orders of magnitude beyond anything our civilization currently produces or even theoretically knows how to harness efficiently. So here is what we have. We have a universe that is so large that even measuring distances within just our local cosmic neighborhood requires units in the trillions of miles. We have a physical speed limit that nothing with mass can reach, and which even approaching requires extraordinary energy. We have propulsion technology that is fundamentally limited by the mass of its own fuel. And we have a fastest spacecraft that would take 17,500 years to cover a single one of those units of distance we call a light year. The Pacific Ocean analogy I gave you earlier, swimming across 7,000 miles at 2 miles per hour, that swimmer is doing roughly 750,000 times better relative to their environment than Voyager 1 is doing relative to interstellar space. I want you to really absorb that comparison. Our fastest spacecraft is proportionally worse at crossing interstellar space than a human swimmer is at crossing an ocean. The ocean is enormous by human standards. Interstellar space makes the ocean look like a puddle on a kitchen floor. And we have not even talked about the energy required to simply decelerate at the other end of the journey. If you accelerate a spacecraft for half the trip and then flip it around to decelerate for the second half, you need just as much fuel on the deceleration side as the acceleration side. That doubles your fuel requirements. And because of the rocket equation, doubling your required fuel does not mean carrying twice as much fuel. It means carrying exponentially more. Every time you try to add performance to a chemically propelled spacecraft, the fuel mass spirals upward in a way that rapidly becomes physically impossible. This is why serious physicists and aerospace engineers who think carefully about interstellar travel do not talk about chemical rockets at all. They talk about ideas like nuclear pulse propulsion, light sails driven by powerful lasers, or theoretical concepts that require energy densities we cannot yet produce. These are fascinating ideas, some of them genuinely promising on paper, but they are also decades or centuries of development away from being testable at any meaningful scale, and none of them come close to solving the full problem on their own. The universe is not hostile to us in a dramatic way. It is not actively trying to keep us confined. It simply does not care about us at all. And it was not constructed with our travel needs in mind. The distances are what they are because of the way matter and energy distributed themselves after the early universe expanded. The speed of light is what it is because of the geometric structure of space-time. Chemical propulsion is as limited as it is because of the laws of thermodynamics and mass conservation. None of these things are negotiable. None of them are going to be repealed. A light year is not a year. It is 6 trillion miles, and getting across even one of them at the absolute pinnacle of human spacecraft engineering would take a civilization longer than it has existed so far. That is not a discouragement from dreaming big. It is a clean, clear mathematical statement about where we actually stand in this universe. And I find that kind of honesty about our situation far more interesting than any comfortable illusion about how close the stars might be. The cosmos is not a neighbor. It is a geometry, and geometry does not make exceptions.